All right, so I'll go through this. This is shorter, but it's kind of interesting to me. All right, so it's not the designated figure that Ala wanted us to show, but this is my concept of workflow models for metabolomics. Basically, we have to use everything that there is available to us. And it's really an iterative thing. Mining the data is really going to be important, unless you're just looking at the levels of coenzyme Q or something like that in a cell. That was for Marine. There's going to be a lot of data in most cases, and trying to understand the data is going to take some time. And so, once you get a data set from, you're not going to know what's happening with it right away, because you have to think about it, remine it, like I said, do ratios, adjust it for different things, and Sharon's going to talk about that a little bit. But it's satisfying in a way that metabolomics, as we talked about the variabilities, we were very upfront about the variability that you get in this data, but it still works. And there's some interesting things that you can get out of data. So this is a data set of rats that were fasted for 24 hours. And this is an untargeted data set, but it proves the point I want to make, is that you can see that if you look at the metabolites, known metabolites that are altered following a 24-hour fast, and you look at this as a Z-transformed data plot, you can see that that the fasted and controls, they mostly overlap. The controls and the fastads tend to separate a little bit, but then there's metabolites that are highly differentially changed under fasting condition compared to the control condition. So these metabolites go up or down in comparison to the median of this. And if you do a heat map of the metabolite levels, what you can find is that you can cluster these different conditions, and you can see across that here are the fasted animals, here are the fed animals here, and they cluster significantly differently. If you look at the control animals, there's some really interesting things, and this is the important point about this, is that you really need to have all your metadata, the data it's associated with. So you can separate the fasted from the fed, but look at this fed group right here. So, these are looking, there's red here, and then in this group, you got a bunch of green in here. And you go back and you take a look at what's the difference of these fed animals versus the other fed animals, is that all these animals were in one cage. And so, but they were all sitting in the same room, getting the same food, and the blood was harvested at the same time and processed the same day and run through the machine and analyzed the same way, yet they're different. And so when we actually talk to the people who are taking care of these animals, this cage, the rats in this cage fought all the time. They were just mean to each other. They actually had to one day separate those guys because they were really beating the shit out of each other. Excuse me. But and so this is a reflection of a behavior, and not a reflection of biology or fasting or anything like this. And so, which is really so. Taking careful notes about where animals come from and those kinds of things are critically important to try and understand. And so, and let's just say that this didn't separate from this. At some point, you can make a decision that these animals were beating the heck out of each other. Maybe they are not representative of these nice docile animals that were in this cage or that cage. And so you can tell this is a different group. And so if you're going to compare things that change fast-fed, or whatever conditions you can do, you need to understand this. But it's also nice when you actually see stuff that you really, 3-hydroxybutyronic acid, palmitoleic acid, all these different things. These are things that are known to go up and down in fasting. And then there's other things that people really never thought about as being those things that might change in fasting versus the fed state. And so, anyways, I just wanted to point that out about, when you find funny things in data, there's usually a reason that there's funny things in data. Okay. The other thing about targeted metabolomics is that you can actually do direct comparisons a lot between different metabolites. And so this is a study that we did, and this is this weight loss clinic I spoke about yesterday a little bit and a little bit earlier, looking at the levels of different metabolites that are related to each other. So remember I said that we believe that the acylcarnitines, those lipids that are generated from fatty acids, reflect the amount of fatty acids that are coming into the mitochondria. So remember I said under high carbohydrate feeding, we get this acylcarnitine 10-1 that goes up, and we believe it's because there's more of this monounsaturated fatty acid that's being de novo synthesized coming in. Okay. So we actually want to do this, and this not exactly that, but I wanted to show you something that's really interesting. It tells us that you can make inferences about one thing by measuring another thing. Okay, and I think this is an important thing. So here's the plasma level of the 18-1 fatty acids. This is the total amount of 18-1 fatty acid when we measure the total amount in the plasma. This is taking triglycerides, the phospholipids, the cholesterol esters, and we hydrolyzed all the fatty acids off of all these lipids and just measured the total amount in the plasma. Arun did this for us. And then we measured also the acylcarnitine associated with it. And then we measured those after we fed people a mixed meal tolerance test where we gave them a slug of Ensure, which causes an increase in glucose levels and increase in lipid level, or excuse me, an increase in insulin levels. Now, what high insulin does in your blood is it suppresses lipolysis and decreases the amount of fatty acids that's coming into the system. Okay? So what's interesting is that if you look at the 18-1 levels and then you look at the cognate acylcarnitine and you look at the patterns, what you can see is that there's a nice correlation in individuals before, after weight loss, before, after weight loss, before, after weight loss, how those acylcarnitines correlate with the fatty acids in the blood. And so what we believe is that if you just measure an acylcarnitine in the blood, you really get a good reflection of your free fatty acids in the blood. And it actually turns out it's much easier to measure a acylcarnitine than it is a fatty acid, just from a technical point of view. And so you can make surrogate measures now and make some inferences. The thing I'd like about this plot, and if you look at enough of these, you actually start maybe imagining things. But look at this person before and after they lost weight. You can see that after you give insulin, their levels went down, and their 18-1 went down. They sort of overlap, but they look like they have either less fatty acid oxidation because they have lower levels compared to these other ones where you actually compare the levels. But the pattern of fall and rise seems to be pretty much consistent in individuals. And so the patterns tend to be similar if you look at the patterns of down and up, even after a weight loss. And we believe that these patterns actually mean something. I have my ideas what they may mean. We also looked at C5 and leucine. So C5 carnitine comes from not fatty acids, but from branched chain amino acid metabolism. Now, when you give somebody a mixed meal tolerance test, the lipids, it takes a while for the lipids to come into the circulation. And so usually you see the fatty acids drop in the blood. The leucine levels, however, go up. So if you give a load of protein, the leucine levels or amino acid levels tend to go up after the meal and then they come back down, unlike the lipids which tend to fall. So what you can see here is that the leucine comes into the system, goes up, down, before and after weight loss, before and after weight loss. Again, this is kind of an interesting guy. Look at this pattern here before and after weight loss. Here's his leucine levels. Doesn't really go up much in him. He's got a high basal level, but it goes down very rapidly. And then the pattern before and after he loses weight seems to be the same. And he also has this very curious change in the carnitine, the associated carnitine, where it goes down in the beginning, then it goes back up, goes down, goes back up. And if you actually start taking a look at these patterns, they seem to have stereotypical patterns this way too. Now, is there some information in these patterns? We don't know what it is yet. But again, by looking at these things and comparing precursor products and things like that, you might be able to infer stuff. And if you look at the ratio of C5 to leucine, it actually correlates with insulin sensitivity pretty well. All right. So this is what I thought was going to show you before. So remember, this is the baseline relationship map. After a weight loss, you can see the relationship map changes. Conversely, if you have, let's see, do that with this. Conversely, if you overfeed a couple thousand calories a day for a couple weeks, you can also change things. And here's the baseline relationship map of I believe it's 9 individuals. This was done in Jeff Horowitz's lab. Before and then after feeding a high caloric intake, which most of it was fatty acids. Now, it's really interesting that these individuals have this sort of high density blocks here, and then you start giving them high fat diets, and it starts breaking them up. It goes back to this whole thing about more fatty acids tend to improve metabolism more than high carbohydrates do, and it's really. Oh, really? All right. Okay, I'm almost done. See, I thought it was going to be like, I was talking slow because I thought I was going to have more time. All right. So then the study, let me go back. This is this high PUFA study that we did. Other ways of looking at the data, if you just take and look at the amino acid levels, after 21 days of carbohydrates and 21 days of polyunsaturated fatty acid diet, you really don't separate them. So probably amino acids are not a great thing that's going to dictate diet. Now, if you remember what we did in this diet was we fed them a standard protein diet or kept protein constant in this study. And so maybe it would make sense. This is just looking at the plot a little bit differently. If you look at the absolute values, you can see that the individuals, there's not much change before and after that. And so your bar graph is not that much different. This is a metaboloanalyst. Is that today? No, tomorrow. Okay. But if you look at isocarotines, remember I said that isocarotines seem to be changing. In fact, isocarotines, if you ran just the isocarotines and looked at the separation, you can see that the carbohydrate and PUFA diet tend to separate very nicely, and that people at baseline are tending towards more the carbohydrate diet. In fact, the people tend to eat more carbohydrates in their diet, at least in this country, and these people are probably no exception. The one big problem we did with this study is we never got their baseline dietary intake, which has been a problem. If you look at the individual isocarotines, you can see 10-1, again, is one that's up a whole lot in the polyunsaturated fat diet compared to the baseline of the carbohydrates. It reminds you of our random forest, which is telling you basically the same thing. This is just a flash of a tool that we're going to show you. This is an early version of a tool called CoolMap that we use, where you can look at a lot of these things in an interactive way with heat maps, and it's actually a great way to mine data. What I show you here is that these are the control individuals at baseline, 4 and 7 days of the 1, 4, 7 days of the polyunsaturated fat diet. You can see 10-1 tends to go down. So here's baseline. This carbohydrate diet. I apologize. So it's down, goes up after the polyunsaturated fat diet, then goes down again. If you look at this, and you can actually start seeing the patterns here. Here's the people with non-alcoholic fatty liver disease. on this diet, you can see there's more red in here than there was at baseline. There's more green here. And even the people with non-alcoholic fatty liver disease show the same pattern. And so it seems to work in even people who have a disease state. I showed you this before. This tool that we'll show you also allows you to cluster things. This is, although we didn't ask the people about their diet at baseline, we asked nutritionists to take the diet that we fed everybody and do a dietary recall as if they had provided the information for the diet, and so blinded individuals who didn't produce a diet. And then we took that dietary recall and we clustered it with the metabolite levels. And it actually sort of works. If you look in this cluster here, this is under the polyunsaturated fatty acid diet feeding. If you look at the, I had this highlighted, the total calories from fat or monounsaturated fatty acid, which correlate together, in a cluster, you can see all the acylcarnitines, and they're negatively related. The higher the levels of the fatty acids are coming into the system, the lower levels of these acylcarnitines that are associated with fatty acid oxidation. We believe that under fasting conditions, which are really, this is reflecting what's going on in the liver, and that the fatty acids are being utilized by other tissues and not as much in the liver, and that's why they tend to be down. And so there's this relationship that we have that's based in the biology. Yes, I'm almost done. If you actually look at clustering, and this is not a great picture, but if you look at the total carbohydrate levels, you can see that the saturated fatty acids are positively correlated with those. They seem to go in the same direction. Again, the more carbohydrates going into the system, the more saturated fatty acids you get. And if we look at the percent grams of protein, even though they really didn't change at all from a statistical standpoint between the different diets, if you look at the correlation, however, of the percent protein in the diet, it's in a cluster with all the amino acids. So now you can start exploring the data a little bit more, saying that, maybe one number is not changed to the other, but the correlations between intake and the amounts are there under a specific dietary condition. So it's getting towards that we might be able to do this, where we can actually take your tube of blood and tell you what you've been eating. Not specifically that you had the bad stuff out there this morning, but interestingly, the aqueous untargeted profiling didn't do a great job of separating these groups. So they tended towards separation, but they weren't as good as we really wanted them to be. But the lipidomics, this is Tanusoni and TM's data using the lipidomics platform, that actually does a pretty good job of separating these individuals. The polyunsaturated, the blue is the carbohydrate. Actually, the green is carbohydrate. Blue is polyunsaturated fatty acids, and you can see the baseline. The reds tend to come over into the carbohydrate space. Lipidomics gives you lots of data, and this is a harbinger of what we're going to see more. One of the things I wanted to point out why this program was really helpful for us is that, so these are people, the control individuals at different days of feeding. And what we found is that there's this outlier here and this outlier here. And they were the same people, the same person. And we went back and looked at the tube, and it looked like the writing on the tube actually got them backwards. So if you actually look at it, and we had independent people take a look at it, we probably misclassified these two people. And actually, just by visually looking at these data sets, you can actually see very rapidly that you might have an outlier. Now, this is just going back and looking at it. What's the right thing to do under this condition? So now we think we did it. So you have to ask yourself, well, do you just now reclassify it because it actually seems like it's much better, or you just throw it out, which is probably, which is what we do when we look at them. There's also an interesting one in here that we found, that we had an individual that was classified as a control, but when we went back and looked at his profile, he actually clustered with the non-alcoholic fatty liver disease. we went back and looked at his ultrasound because we did ultrasounds on all these people, had the ultrasonographer read it again. He says, oh, no, that's not 5%. That's more like 9% fat in the liver. And so they retrospectively reclassified this guy on the basis of our metabolomics profile. Now, what do you do with that data? Well, the original classification was a control individual. And so, again, how do you reconcile these things when you actually present data, which is that. So summary, these are the people who did all the work, and I'll be glad to answer any questions. We're going to take a break first. Answer questions first. Anyways, I just wanted to give you a flavor of now taking targeted data, mining it, putting it together with other data sets, looking at the transcriptomics data. I didn't show you, you can actually, with Ola's program, take, which you'll learn about Metscape, you can take the transcriptomic data, you can overlay it with the metabolomic data, you can actually start finding pathways that are related to these different metabolite levels and making inferences as well. I think it's cool. All right, so what time should people come back? 10 minutes? You're holding up 5. And then we'll have Shervin teach